All right, if you're getting ready for your Week 1 Applied Physics exam, then you are in the perfect spot. We are about to break down everything you need to know. Think of this as your focused, no-fluff blueprint for the test. Okay, let's get into it.
First things first, let's just take a second to see what's really on the line here. Your midterm and your final. I mean, together, that's a massive 70% of your entire grade. That's exactly why we're here. We're going to make sure you are totally rock solid on these fundamentals from day one. Because mastering this week's material, that's your first huge step to acing those big exams.
So, here's our game plan. First, we're going to learn to speak the fundamental language of physics. Then, we'll load up our essential math toolkit. From there, we'll dive deep into the core concept of vectors, learn how to describe motion, and then we'll put it all together to crush a classic exam-style problem. And we'll wrap it all up with a final checklist of everything you got to lock in. Okay, Section 1. Physics Fundamental Language. Look, before we can solve for anything, we have to be speaking the same language. And in mechanics, that means knowing the basic quantities and their units. You know, in classical mechanics, it's kind of wild, but everything, and I mean everything, just boils down to these three basic quantities: length, mass, and time. Their official standardized SI units are the meter, the kilogram, and the second. Every other thing we're going to talk about, like velocity or force, is really just some combination of these three. They're the ultimate building blocks.
So what exactly is a meter? Well, it's not just some random length anymore. The modern definition is incredibly precise. It's tied directly to a fundamental constant of the universe, the speed of light. A meter is officially the distance that light zips through a vacuum in a teeny tiny fraction of a second. Pretty cool, right?
Now the kilogram, this one's fascinating. For over 100 years, the standard for 1 kilogram was literally a physical object, a special metal cylinder tucked away in France. Now, of course, the problem with physical objects is that they can change, even just a tiny bit. So while the cylinder was the standard for a long time, scientists have since updated the definition to be based on a fundamental constant, just like the meter, to make sure it's stable and universal.
And finally, we have the second. This unit is defined with just mind-boggling atomic-level precision. It's based on the oscillations of a cesium atom. And if that sounds familiar, it's because this is the exact same principle that makes atomic clocks so unbelievably accurate.
All right, we've got the language down. Now it's time to open up our essential math toolkit. This is where we grab the tools we need to translate those physics concepts into equations that we can actually solve.
To describe where something is in space, you basically need a map. And in physics, we use two main kinds. You've got the Cartesian system, which you know and love, right? The good old XY grid, like streets in a city. But then there's the polar system. It does the same job, but in a different way. It uses r, theta. That's a distance from the center and an angle. Both are super important for describing position.
Now, for your exam, you absolutely have to know how to jump between these two systems. It's non-negotiable. So, to go from polar to Cartesian, meaning you have a distance r and an angle theta, and you need the x and y parts, you just got to burn these into your brain. The x component is always r times the cosine of theta, and the y component is always r times the sine of theta.
And what about going the other way, from Cartesian back to polar? Just picture it. Your x and y components make the two sides of a right-angled triangle. The total distance, r, well, that's just the hypotenuse. So we use the Pythagorean theorem. R is the square root of x squared plus y squared. And to get the angle, theta, that's just basic trig. The tangent of theta is opposite over adjacent, or y over x. So theta is just the inverse tangent of y divided by x. Simple as that.
All this math with coordinates and angles leads us straight into our next topic. And honestly, this is probably the single most important concept from week 1, vectors. So much of physics isn't just about how much of something there is, it's about which way it's going.
So what's the big difference between a scalar and a vector? It's really simple. A scalar is just a number, a magnitude. It's a size. Think about mass or the speed of your car. A vector, on the other hand, has both a magnitude and a direction. Think velocity, 60 miles per hour north, or force, pushing with 10 pounds downward. On your exam, you have to know this difference, because mixing them up is an easy way to lose points.
And this right here, this is the most critical skill you need for vectors. It's breaking a single vector down into its simple x and y parts, or components. Why do we do this? Because it's a total game changer. It turns one tricky diagonal problem into two super easy straight line problems. And it's a simple 3-step process using the exact same trig we just covered.
Okay, so now we can take all these tools we've gathered and apply them to our first major area of physics, kinematics. This is basically the branch of mechanics that's all about describing motion. It's the official vocabulary of movement.
Here's a really crucial point you have to get right. Displacement is not the same thing as distance. Not at all. Distance is a scalar. It's the total ground you covered. Displacement is a vector. It's just the straight line change from your starting point to your ending point. Think about it. If you walk in a 5-meter circle and end up exactly where you started, your distance traveled is 5 meters, but your displacement is 0.
All right, theory time is officially over. Let's roll up our sleeves and put everything we've learned together to solve a classic problem. This is the exact kind of multi-step vector question you should expect to see on your exam.
Here we go. The hiker problem. She walks for 2 days, which means we have 2 different displacement vectors. Our job is to find her total displacement. In other words, we need to find that one single vector that points from her absolute start to her absolute finish.
Okay, step 1, let's deconstruct day 1. The direction is southeast. Now, in math terms, on a coordinate plane, that's an angle of -45 degrees from the positive x-axis. So we just plug that into our component formulas. The x component is 25 times cosine of -45, which gets us a positive 17.7 kilometers. The y component is 25 times sine of -45, which is -17.7 kilometers. Easy enough.
Now for day 2. This one's a little more straightforward. The direction is 60 degrees north of east, which is just a nice positive 60-degree angle. We run the exact same play. The x component is 40 times cosine of 60, which gives us a clean 20 kilometers. The y component is 40 times sine of 60, which comes out to positive 34.6 kilometers. And here's the magic of using components. This is why we do it. To find the total displacement, we don't need to throw out any complicated triangles or use fancy geometry. We just add up the x's and we add up the y's. It's that simple. Our total x displacement is 37.7 kilometers, and our total y displacement is 16.9 kilometers.
We are on the home stretch. Now we just use our Cartesian to polar conversion formulas to turn these final x and y components back into a proper magnitude and direction. The magnitude comes out to 41.3 kilometers. The angle is 24.1 degrees, and since both of our final components were positive, we know that direction is north of east. And that is our final answer. We solved it.
So let's do a super quick recap. Here's your final exam checklist for this week. 1. Master those SI units, meter, kilogram, second. 2. Know your coordinate conversions cold, both ways. 3. Memorize those vector component formulas. 4. Make sure you understand how to add vectors using components. And 5. Never, ever, ever confuse displacement with distance.
You know, we've spent this entire session learning how to precisely describe motion. You now have the vocabulary, you have the math, you have the tools. But this brings up the next really big question in physics, doesn't it? What actually causes motion in the first place? And that is a story for next time. Good luck with your exam.